Good morning, class. Mr. Manta here. Today's date is Wednesday. This is Wednesday, April 1st, 2020. And you might be thinking, hey, this is April Fool's Day. Is today's lesson an April Fool's joke? My answer to you would be absolutely not. Today's lesson is a real lesson. It is a bonus lesson, though. We just took our quiz and finished our unit on light. So before we go starting a new unit, we're going to have a couple bonus lessons. This is because next week is spring break. And I didn't want to start a new unit right before spring break and then have to ask you guys to remember a whole bunch of fundamental stuff like a week later after having no class. And so instead, today we're going to have a bonus lesson. And what today's bonus lesson is actually going to be on is this very, very, very famous scientific discovery that E equals mc squared. You've probably heard of it before, but you probably don't have a great idea of what it means. Today, we're going to learn what the heck E equals mc squared means, and how it very actually quite perfectly follows from all the stuff we've been learning about energy and light in these past couple of units. Now, anyone, and I do mean really anyone, can probably tell you that E equals mc squared. People love to say this just kind of as like a thing that you can say that makes you sound smart, even if you don't know what it means. You have lots of smarty pants kids, and even grown-ups too in the world, who will tell you E equals mc squared, and as if that justifies it, like they know a whole bunch of stuff because they know this thing that's known for being a thing that smart people say. Really what they're trying to take credit for is this discovery made by this fellow right here, Albert Einstein. Albert Einstein is the one who discovered E equals mc squared, and because he is known famously across the history books as maybe one of the smartest guys that ever lived, people try to sound smart by talking like Albert Einstein. But a lot of the times people don't actually know what it means, what they're saying when they say E equals mc squared. I'll show you an example. Now, if you're a Purdue student, then you watch this movie with me in indoor recess, but if not, let me get you caught up real quick. To show you an example of the way people like to use this E equals mc squared thing, this is a scene from a movie called School of Rock that I'm a big fan of. This guy right here, being played by Jack Black, is pretending to be a teacher. He's tricking the principal out of school and pretending to be a teacher with all these kids while really teaching them to have a rock band. He's going to put on a fake lesson for the teacher that involves E equals mc squared. Watch closely.
And we shall teach rock and roll to the world. There's no way you can stop the School of Rock.
Stop! Big red alert, Mullins. What's going on?
So the principal is coming. He needs to convince the principal that he wasn't just playing guitar in class, he was teaching them math. So
Come on.
And therefore, E equals mc squared.
oh, would you look at that? What an advanced lesson he was doing on this whole E equals mc squared thing, isn't it? Too bad that all this math over here is just absolute nonsense. Again, this is the kind of thing that a lot of people like to talk about to show off how smart they are, but it doesn't mean anything if you can't actually tell anyone what it means. So, today, this kid and Jack Black over here are going to get exposed. We're going to find out what it really means and how it's not maybe what you think it might mean. Alright. Today, we're going to learn what Einstein discovered when he discovered this formula E equals mc squared. Now, some students and even some teachers in the world might freak out at this thought because E equals mc squared is this really advanced topic. There might be some other teachers saying, but Mr. Manta, you can't teach E equals mc squared to 5th and 6th graders. Most people learn that in college, and they're freaking out like this guy right here. Well, what I would tell them is that they don't know the kind of stuff that we've already been learning in science class, and they haven't met you guys. You haven't met these 5th and 6th graders. Because I'm pretty sure that my 5th and 6th graders can handle this very advanced topic. And besides that, today is a bonus lesson, right? So we're going to get a chance to see what it's all about. Alright, here's the deal. When somebody says E equals mc squared, what they are telling you is a formula. We've already seen lots of formulas in science class before. For example, this one over here. This should look pretty familiar to you because we just finished a unit on energy, and this was our potential energy formula. It was PE equals M times H times G. And you guys should be able to tell me that that means potential energy equals mass times height times gravity. So, just like this is a formula, this here is also a formula. The other example that we saw was the kinetic energy formula. You guys could probably all tell me that this means kinetic energy equals 1/2 times mass times velocity squared. This is the E equals mc squared formula is really not that much more complicated than these two formulas that we're seeing here. But the stuff that it means, or is like the implications that we're going to talk about, are the reason why it's considered really complicated and really advanced. So, just like this is a potential energy formula and this is a kinetic energy formula, you could refer to E equals mc squared as the rest energy formula or as a total energy formula. We'll talk about exactly what that means in a bit, but suffice to say for now, rest energy is a kind of energy we've not talked about before, and it usually doesn't get talked about very often unless you're talking about very advanced physics. But it is the energy that an object has purely for existing, for with having the mass that it has and existing in the world. That should make more sense in just a moment. So, now that we know that, like in this formula, PE is potential energy, M is mass, H is height, G is gravity, what do all the things in E equals mc squared stand for? Well, some of them are going to look pretty familiar. E, we've already talked about before, you probably could have guessed, stands for energy. In this formula, just like our other ones, energy is being measured in joules. M, you could probably guess too. M stands for mass. And just like in our other formulas, mass is being measured in kilograms. Lastly, c squared seems like this unusual one, but even c squared is something that we have already talked about in science class. C stands for the speed of light. It's being measured in meters per second, and just like velocity in the kinetic energy formula. And the reason why the letter C is being used instead of you would think you do SOL for speed of light maybe, is because Einstein picked this letter C because C is constant. It's a number that never, ever, ever, ever changes. It's always the same speed, the speed of light, no matter where you go in the entire universe. And so C stands for constant, but really what it means is the speed of light. Lastly, it's also important to remember in this formula that C is being squared. We already talked about what it means to square a number when we were doing the kinetic energy formula. It means that the speed of light is going to get multiplied by itself. So 2 squared is 2 times 2, which is 4. 3 squared is 3 times 3 equals 9. This is going to be the speed of light times the speed of light. So it's going to be times itself. It's going to end up being a really big number. All of these things, energy, mass, and the speed of light, are stuff that we've just had science units on. So at this point, you guys should be feeling like, we got this. This is solid. You can understand this formula just like a college student. Alright, now if we take that speed of light, this C number, and we plug in the actual speed of light, because after all, it never changes, what you would get is this. The speed of light is, in meters per second, 299,792,458 meters per second. Maybe you're starting to get a sense of why Einstein shortened it to C instead of spreading out that number every single time. If we want to take that number and actually square it, actually multiply it by itself, it gets even bigger. Now C squared is going to become this huge giant number, because we just had this number times itself, and you get this number. If you were to say this entire number out loud, it would be 89 quadrillion, 875 trillion, 517 billion, 873 million, 681,760 meters per second. It's just a really big number. At that point, you can probably understand why Einstein wanted to shorten this to c squared, because he didn't want to say 89 quadrillion, say it every single time. And that, ladies and gentlemen, is the formula. E equals mc squared. Energy times mass times this number. That's all it is. We can use that formula, just like we use the potential energy and the kinetic energy formulas, to solve word problems like this one. This brick has a mass of 2 kilograms. How much rest energy does it have? Well, just like we used our potential energy formula, we can take that mass and plug it in for M, and we know what C is, and we're going to be able to calculate its rest energy. The formula is going to look like this. Rest energy equals 2 times this really big number that we learned is always going to be c squared. If you do that multiplication of 2 times 89 quadrillion and all this, you'll get your final answer pretty easily. If I'm going to read this one out loud, we learned that this brick has a rest energy of 179 quadrillion, 751 trillion, 35 billion, 747 million, 363,520 joules, because we always measure joules in energy. Just like that. The number is really big, but the basic way that you use the formula is not any more complicated than any of the formulas we've already used. The question is, well, what does it mean that this brick has that much rest energy? Like, in class we learned that maybe something will have gravitational potential energy because it's high up and it could fall and it could use that energy. Or something will have kinetic energy because it's moving, right? Or maybe something will have thermal energy because it's hot. What does it mean that this brick has rest energy just for being there? It means that it has energy just in virtue of the fact that it exists. That there is energy inherent in mass. And just for having a mass of 2 kilograms, this brick, this matter itself, has energy that we call rest energy. And we just calculated it. As you can see, rest energy usually ends up being a really, really big number. So even if this brick also had some thermal energy or some kinetic energy because it was moving, most of its energy, and pretty much most of the energy that any object has, is going to be rest energy because it ends up being such a huge number. And ta-da! That's all it is. That's all there is to it. We just use that formula the same way that we used all of our other formulas. Now at this point, you might be wondering, well, what's the big deal? Why is Einstein so famous for coming up with this formula? Why did he win a Nobel Prize? Why do people talk about it and make themselves sound smart? Why is it so much more important than all the other formulas? It seems like this formula, for coming up with this one, Einstein has whole crowds of people cheering and applauding him for being so smart. But maybe you're feeling right now more like this woman. Not that impressed. It's just another formula, and in fact, it's pretty simple to use. What's the big deal? Here's the big deal. What's amazing about Einstein's formula is not the equation itself, but what it means. What it means, and what he discovered when he made it into a formula, is this. It means that mass and energy kind of are the same thing. Mass and energy are kind of the same thing. This idea would have sounded crazy to anyone before Einstein. It still sounds kind of crazy now. But he figured it out and figured out that you could use this formula to compare them, and that mass and energy are kind of the same thing. So for example, if I were to have you look at these two pictures and ask you which one of these things is a picture of mass and is a picture of energy, you'd probably say that this brick over here is mass, and this kind of plasma toy with all the lightning shooting around is an example of energy. But you wouldn't exactly be correct. Really, both of these pictures are a perfectly good representation of mass and energy because mass and energy are the same thing. You could say that this brick is a picture of mass, or you could say it's a picture of energy. You could say that this plasma is an animation of energy, or that it's an animation of mass. Because mass and energy are kind of the same thing. This fact, and that's what's really important about E equals mc squared, is this thing called mass-energy equivalence. It means that mass and energy are equal. If you try to go on Wikipedia and look up E equals mc squared, you won't find a page on E equals mc squared. Instead, it will take you to this page on mass-energy equivalence. Because what's really important about the whole E equals mc squared thing is this idea that mass and energy are kind of, in this really hard to wrap your head around way, the same thing. This is how they describe it on the Wikipedia page. They say, in physics, mass-energy equivalence is the principle that anything having mass has an equivalent amount of energy, and vice versa, with these fundamental quantities directly relating to one another by Albert Einstein's famous formula E equals mc squared. This is what's so important, and this is why Einstein is so celebrated, why people have so much renown for him in this discovery, because he discovered that mass and energy can kind of be treated like the same thing. Now, here's where it gets really crazy. This means that if you change the amount of energy an object has, you also change the amount of mass that it has. I'll give an example. Imagine that you go to the coffee shop, down to Starbucks, because, you're having to work from home, you got to get your coffee to fuel yourself. Some of you I know like to drink coffee. And you order a piping hot black coffee. And they serve it to you, and if you were to put a thermometer in it, you would find that that coffee is very, very hot. In other words, it has a lot of thermal energy, because we know that things that are hot have thermal energy. Now imagine that you forget to drink your coffee, and some time goes by, and eventually that coffee cools off. And now it's all cold, it's not as good to drink anymore, and it has less thermal energy because it cooled off, and it sent all that heat out into the world around it. It cooled off, it lost all its heat. Well, we already know that you've transitioned here from having more energy to to having less energy. That makes sense. We've already talked about that. What Einstein is saying is that you also, in this case, have gone from having more mass to less mass. What that literally means is that if you took this exact same cup of coffee that you had here, and the only thing that changed about it is that it cooled off, the coffee wasn't as hot anymore, but you have just as much coffee, and you put it on a scale, it would actually weigh a tiny, tiny, tiny bit less, because the energy that it has is mass, and mass is energy. This coffee has lost not only energy, but mass as it has cooled off. Another example, you can go the other way around too. If you give, like in this case, we saw that if something loses energy, it loses mass. Well, the opposite is true too. If it gains energy, it gains mass. So imagine that you have a wind-up toy. I know he's looking kind of scary, but this is a monkey wind-up toy that you can, there's like a little dial in the back, and if you turn it, if you put energy into the system, then it will start bouncing around and slapping its cymbals together. So this thing here has no kinetic energy because it's not moving, and now it has a bunch of kinetic energy because it's moving around all the time. In this case, you would agree with me, we already know that we went from having less energy, kinetic energy, to having now more energy. What Einstein is saying is that the monkey on the right also now has more mass than the monkey on the left. And in fact, if you had a super precise scale and you put each of these monkeys on a scale, you would find that this one weighs a tiny, tiny, tiny bit more than this one because of the energy that you have added into this system. Mass is energy. Energy is mass. They affect each other. They are the same thing in a certain kind of way. We just think of them really, really differently. Now, because of how the formula works, it means that you have to make a really huge change in energy just to get a teeny tiny change in mass. The reason for that is because this is the formula, right? E equals mc squared makes this big number. And if you do the algebra of this, basically means that if you make your energy go up, like if energy goes from 100 joules to 200 joules, and you want to figure out how much that affects the mass, well, you'd have to divide your energy by 89 quadrillion 875, that giant super number, basically. That's not super important, but the basic way it works out is that if you raise energy a ton, like a huge gain in energy, you only make a teeny tiny difference in the amount of mass that something has. But the flip side is also true, which means that if you make even a teeny tiny change in mass, it can cause a huge change in energy. You can get just a little bit of mass, you can get a ton of energy out of. Here's an example of that. You might be thinking, how much energy could you really create if you turn all of your mass into energy? How about like the amount of energy in the sun? I mean this for real. The place that the sun gets all of its energy from is from changing the mass that it has from mass into its energy form. This gets really complicated, and we don't need to know all of it right now. But the idea is the sun turns its mass into energy through a process called nuclear fusion. It is constantly taking little bits of sun every single day and taking to this process called nuclear fusion that's converting them into energy it can radiate out and shine out into the solar system. Now, these people have done all the really complicated math to show exactly how that happens, but we don't really need to know all the details of that. What we do need to know is that the energy all the energy that's making from nuclear fusion shines out into the solar system. The sun gets a little bit lighter every day that it shines, because as it's sending out, it's losing all that energy. It is therefore losing mass, because energy and mass are like kind of sorta the same thing. As it's losing energy, it's losing mass. In fact, every single day, the sun gets about 350 trillion kilograms lighter. Now, that might sound like a lot to you and me, but that amount is like nothing to the sun. The sun stays almost the same size every single day, but it does lose this much mass because it's sending it out in the form of energy. The same basic idea, too, of how the sun works is also how nuclear bombs work. And it's the reason why nuclear bombs can be such a small little bomb can be so powerful and create such a huge explosion. Because nuclear bombs use a process called nuclear fission that's very similar to fusion. This is why a lot of people say that Einstein helped invent nuclear bombs, even though really he never actually worked on them at all. He never came anywhere near a nuclear bomb or published any research about how to make or how to invent a nuclear bomb. But he did discover this basic idea that mass and energy are the same thing, and you can kind of turn things from one form into another. And that eventually led to the creation of the nuclear bombs, even though he didn't build them himself at all. Alright, that's the information that we had today. Also, since we have one more day of science before our break, we do got a test tomorrow on this. It's going to have 2 parts to it. Your first part, you're going to be asked to summarize Einstein's theory of special relativity and contrast it against the paradigm of Newtonian physics which preceded it. Discuss the historical significance of Einstein's contribution and alternative trajectories for world events had it not occurred. Second part, use the stellar luminosity to determine the mass of the star Etna Canis Majoris, an Alpha Cygni variable class Ia luminous supergiant. Using the mass, then calculate the amount of rest energy intrinsic to the star using Einstein's E equals mc squared. Convert that energy to calories so that we can put it on a menu. We can have a star on our menu. As long as you can do those 2 pretty quick things, you'll be good to go for the test tomorrow. Alright, that's all we had for today. We're going to go ahead and hop to exit ticket time. Yes, there is an exit ticket for today, and there is also independent work. And this is today's cool thing. It's a video from NASA that makes me really excited about space travel. It's called How We Are Going to the Moon 4K. I'm going to try to link it right here. That may or may not actually work. But if it does work, then that's fun. You can just watch it right there. If not, go ahead on YouTube and you can search it if you're curious to watch this really cool video from NASA. Our independent work for today, let me show you. Our exit ticket for today is right here. Our independent reading is a link right here. And you're going to have some independent questions to fill out as well. Oh, and by the way, that whole test that I had mentioned, April Fools. That's not going to be a real thing. I'm not going to test you guys on this concept, especially with those questions. Goodness gracious. Right after learning this after just one day. There's no test tomorrow. We'll probably have another bonus lesson, and then you guys are off free for spring break. That's all we got for today. Take care.